We've already established what Aufbau's principle is for determining electron configurations. This is where in the last video we looked and we said 1s2, 2s2, 2p. It's the order at which you're filling electrons. So 3d comes before 4p. But are there exceptions to the general rule, that stair-step pattern that you saw previously? You know this is chemistry. There's always rule breakers. Okay, so let's look at some of these exceptions. I'm not going to be interested in you memorizing all these exceptions, but I am interested in can you figure out which one is an exception and then think through why that exception might exist. The concepts and understanding of why are more important than pure memorizing. All right, so I found this periodic table on Spectrum Chemical website. Actually, I think I got it at a trade show and they gave me this periodic table and I loved it. So at a conference, and I loved it. It's been my favorite, especially for this because they tell you the electron configurations for pretty much every single element except these new ones. So you can find this periodic table on their website. If you just Google Spectrum Chemical and the words periodic table, it'll show up. I did fix some things. Cerium's electron configuration wasn't correct, so I changed that. And then I also added the names for elements 110 through 118, which you see here below. Yay, Tennessee, something named after Tennessee. So that's fun. But I have given it to my students, but if you're not a student, you can look here and you can find it. All right, so what I want us to do is in the box, there are 8 exceptions. Are there other exceptions elsewhere outside the box? Absolutely, but let's just, for the sake of this video, focus on the 8 exceptions in the box below. So I'm going to work through how do you figure out if something's an exception? What does that even mean? And then we're going to figure out why, or at least think through why that might be an exception. What makes sense and why, stability-wise, we might need to actually change the electron configuration than what it normally is. So here's a zoomed in view if you want to look at it a little bit closer. I know it's sometimes hard to see off that previous image. All right, so let's do krypton first. Is krypton an exception to Aufbau's principle? Spoiler alert, it's a noble gas. Noble gases are very, very stable on their own, so the answer to the question, is it an exception, is probably no. But for the sake of this video, let's pretend we don't know. So what do I mean by that? If we were to write the electron configuration for it, we would follow the general step of 1s, 2s, 2p, etc. Let's do that. 1s, 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p6. So if we reorganize it and put it into shorthand configuration, that would be argon with a 3d10, 4s2, 4p6. Does this match what you see here in your periodic table? Yes. So that means it's not an exception. So this Aufbau's principle is allowing us to predict these electron configurations. But experimental evidence can come in and prove this prediction wrong. And when it does, we have to rethink through why it might have been differently. So to do this, let's look at the element chromium. The first thing I want us to do is to draw out the electron configuration. I'm going to give myself a little more room, so I'm going to start over here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. So if we put this in noble gas configuration, argon has all the way up to 3p6, so it'd be argon, 3d4, and then 4s2. Does this match what is shown on the periodic table? No, it doesn't. It doesn't at all. So why not? Okay, like I said, experimental evidence proved that this is a more stable configuration. So remember, all of these things are just predicting where electrons are going to go based on stability. And so stability-wise says it's actually more stable to have 5 in the D shell and 1 in the S. In order to think through why this is, it's helpful to write out the orbital configurations. let's draw the orbital configuration for these. The argon, it's not really going to be important. That's going to be the same as what's up here. So the argon part is fine. Let's leave it alone. Let's draw the orbitals here for 3D and 4s. So 4s has one orbital. A D, how many orbitals does that have? Remember, S is one orbital, P is 3, D is 5, and then if I still had showing you the F would be 7. So we've got 4s, and then we have 5 d orbitals. And all of these are in 5d. So what typically happens based on how we predict it is we put one electron up, one electron down in 4s. And then in 5d, we have 4 electrons remaining that we can place in here. Well, what happens here is we have one of these D's are extremely unhappy. And so what I mean by that is these 4 are happy. They have 1 electron each, but wouldn't it be more stable if this also had a resident? It's sort of like as if you're, got a whole bunch of homes out for rent. You want all of them to be occupied. Electron orbitals and subshells are the same way. The D would prefer to have 1 electron in either one, or it would prefer to have 2. But since there's not enough for 2, it'll be fine with 1. And so what happens is it says, hey, S, I'm going to steal 1 from you because you might be more happy, or at least I might be more happy if I take 1 of your electrons. That 1 electron from the 4s comes over here to the 5d. And so how do I know this is a more stable electron configuration? Well, experimental evidence. But what this means is that it's more stable to have electrons in the D5S1 than it is to have 2 electrons in S and 5 into D. So if I were to ask the question, why do exceptions exist? And the reason is electrons always want to enter in to the least stable energy configuration, which is why noble gases are always so stable. And so for chromium, its lowest stability for where it puts its electrons is 1 in S and 5 in D. And so this is an exception to the Aufbau principle because this is what we expect. This is what we get. All right, so I want you to look through. All right, so I want you to look through this box right here and find 8 of them. I already found the one for you, chromium. Okay, hint, S's and P's are normally pretty stable. D's, not so much. They're all a bunch of thieves. F's, also lots of thieves, okay? But check just within this box and see if you can't find a total of 8 exceptions.